Okay, so we got just a couple more classes together here. And we got just a couple more topics that we need to get through with the organic chemistry stuff. I need the first thing we need to do is tell you how I've been lying to you guys all along, but you guys probably figured that out already.
You liar.
I know. What can I say? Right? And then we'll talk a little about things called functional groups. Right? And we'll learn a little bit more about just how we can draw different structures and let's say a shortcut way of drawing organic molecules is what it is. So just a couple of things we'll get through here and learn a little bit more about just how to represent organic structures. Right? And that's really what we're just going to be focusing on for this, let's say, portion of the class. We'll talk a little bit about the representation of it, and then, when you guys move on, or if you move on to organic chemistry, that's where you have to learn all about the, let's say, the function of it, the reactions, and these kind of things. Let's see. So I did remember to actually put the quiz up for you guys, so don't forget to do that. I think you guys have all day to get that done today, right? So it's very difficult. It comes directly from the textbook. You guys will need your textbook though, so just make sure you guys have your the appendix E there, or somebody to look up some of the redox half reactions. Right?
What if I've had my appendix removed?
And see if you can borrow it from my friend. That's how life works, right? But I think other than that, that's all we really needed to chat with. I don't think there's anything else to do. You guys are done with lab, right?
Yay!
So we got lab done, almost done with the lecture, and then we just got the final exam. And then that's it, right? You guys have the summer to forget everything before you come back and start it all over again.
Do you have so little faith in us?
Yes. I'm not gonna lie. Anyway, no, I'm good. You guys will be okay. All right. Anyway, let's get started with prayer then, and then we'll launch into it. But Lord, we thank you. Lord, we thank you yet again that even and especially when just our hearts are troubled and our minds are distracted and our thoughts are just everywhere, Lord, that we know that the best thing we can do is just turn to you, Lord, and just spend that time just talking with you and just sharing what's on our heart and our mind, Lord. And we know that you know these things, but you want to hear from us also, Lord. We know that you're our Father in every aspect of that word, that you just want to spend that time with us also, Lord. And so we just pray that we just increase our faith and just put that spark in our hearts, Lord, in our minds and in our spirit, just to want to spend that time with you, or just help us to humble ourselves to lay our troubles before you, Lord, and just leave them before you, because you said that you would help us with them, Lord. So we just pray that you open our understanding about these things and just grow us today, Lord. Just pray this in your name. Amen. All right. So this is what we had talked about last time, right? We had talked about how to draw let's say the most basic of organic structures. We had made a couple of important observations about how carbon and hydrogen work. Okay, we said that carbon chains, right, we can bond carbons together, and that we will always see hydrogens bound to carbons. Well, I should be careful, not always, right? There are some exceptions, right? But for the 99% of the time when we're dealing with the undergraduate organic chemistry, right, we're going to see hydrogens bound to carbons, and that hydrogen and carbon are friends, and we'll talk about why that's important in just a minute, right? We learned a little bit about things called structural isomers, where we can have the same formula, but we can move carbon-carbon bonds around to make different structures themselves, okay? And so we talked about a little bit about isomers in there. We're not going to go into in-depth study of isomers. Well, again, we'll talk about that later in the next semester, right? But there are different types of isomers, and that will kind of be what the first part of the chapters that you guys will learn in organic chemistry will cover, right? But for the most part, what we need to pay attention to is just how are the carbons bonded to each other is what it is, okay? Cool. And the last thing we talked about is that these things are alkanes. And we said that when we're looking for an alkane, what we have is all the carbons are singly bound to other carbons. Right? That's what the definition of an alkane is, right? We only have carbon-carbon single bonds. So you can probably start to see where the next set of definitions is going to come from as we change the nature of carbon-carbon bonds, we move into different class of structures, right? And we'll talk about that in just a second. Let's think here for a second. A couple of points to make. So I'm just bringing down stuff from the previous page there, so you don't have to worry about necessarily recopying everything. Okay, so we went through and we drew the structure for these three compounds, right? CH4, right? C2H6, C5H12. Okay, so we learned about isomers and all this kind of stuff, good. Let us instead then, let us try and draw the structure of C2H4, okay? And see what you guys can come up with for C5H4 and C5H10. That one's okay. That one's fine. Oh, you're missing hydrogens, right?
I'm still drawing the hydrogen.
Oh, okay. So, exactly, right? So how could we, so remember what one of the things we have to do is count how many total electrons there are. You'll see you should be missing like 2 extra electrons in there. So, and that's gonna tell us whenever we're deficient of it, right? We'll just end up making another line. Similar to what we talked about when we were going through the steps for drawing a Lewis structure last time. C2H4, right? We know that the carbons are going to be bound to together, right? They're going to be bound together at least. And we have 4 hydrogens to deal with, so let's put them around. Okay. So what do we see when we have this issue at least? What's missing? Problem with what we have drawn at least.
Octet.
If you count the total number of electrons there, right? We're bringing in 4 from each of the carbons and then 4 from the hydrogens. So you got to make sure that we account for all of our electrons when we draw our Lewis structure. Got it? So what we can say is that we can start to see carbon-carbon double bonds, right? And that's going to move us away from an alkane into what we call alkenes, right? So alkenes to alkenes. Okay, so the ENE versus the ANE, right? So put a little asterisk. No, you're over octeted one of your carbons. The one carbon has got
dang it.
6 bonds to it.
Right, thanks.
Okay. So we got that, C2H4, that's not too difficult, right? So we go to C5H10. Well, we could start by trying the logical thing, right? Let's put 5 carbons in a row, right? And then we could try to fill in the electrons around, excuse me, not the electrons, the hydrogens around it, just like what we did with the C5H12, right? So let's just start to fill things in. Let's see what happens. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? Huh. Well, we have a problem, don't we? What's the problem?
You won't be able to fill carbon.
Yeah, right. We got a couple of issues with the bonds that we can make in between, or excuse me, that the carbon's missing some bonds to it there, right? So what could we do then? Oops, I put too many in there, didn't I? That's 11, isn't it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, there it is. Sorry. let me first correct myself, right? Yeah. Yeah, that was looking better, right? Let's think for a second. What's the difference between C5H12 and C5H10?
2 hydrogens.
We're missing 2 hydrogens. Essentially, we're missing what? 2 bonds, right? 2 bonds between carbon and hydrogen. Got it? Well, if we can't make bonds between carbon and hydrogen, what can we make extra bonds in between?
Carbon.
The carbon and carbon. Got it? So what we could do, right? What we could do is, let's say we have our 5 carbons. If I add a double bond here, right? Let's go through and see what that does in terms of how many hydrogens I need, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right?
I overthought it.
We okay? So first,
Wait, no, the carbons are still not following, we need, oh, yes they are. I'm brain dead.
no, it's a good question, right? The first question is, hey, are these things all following the octet rule, right? So these out here, right, this is kind of similar to what we discussed before. Remember this carbon here, 1, 2, 3, 4 bonds around it, 1, 2, 3, 4 bonds around it, right? So we have a combination of a double bond and then 2 single bonds to fill up the octet for each of those carbons. Okay, same question here that I like to. We could go on and give a couple more examples, but I think we can draw a conclusion here. What do we notice about the formula, right? The chemical formula for these alkenes versus the alkanes.
1 double bond.
Okay, but the actual formula, like the C5H10 versus C5H12.
It follows the formula C.
For every 1 carbon, there's 2 hydrogen.
Right, so if we want to say a mathematical equation here, right?
CnH2.
Okay. So what we would say is that we have C, right, N, right, and H, 2N. Got it? So if I have C6, right, if I have C6, and I have 12 hydrogens, so I have double the number of carbons, right? So C6H12 would tell me that I have a deficiency, is what we would call it, a hydrogen deficiency, okay? Now, what does it mean to be a hydrogen deficiency? Well, we just don't have enough hydrogens around to what we would say saturate the carbons, to put the maximum number of hydrogens around each carbon. You guys with me on this one?
Wait, so CnH2n, does that follow for all alkenes?
That's what I'm getting to. The answer is yes, but it also can tell us something else. And I'll mention it in just a second, right? But for the moment, that's perfectly fine, right? So every alkene will have that formula, but not every one of those formulas will be an alkene.
Oh, okay.
That's gonna be the difference. Good? Now while we're at it, so if for an alkene we have CnH2n, how do we get to C5H12 then? So we have CnH2n plus how do we get from 10 to 12? You have to add 2, right? So what's the generic equation for every alkane? CnH2n plus 2, right? So generically, what does this say? An alkane, another word for that, is a saturated hydrocarbon, right? It just means we have the maximum number of hydrogens that we can fit around all of the carbons. As soon as I take 2 hydrogens away, we make things called unsaturated hydrocarbons. But you guys have probably already seen that terminology around, right? You read your nutrition label, and what does it say there?
Saturated fats
Saturated fats and unsaturated fats. Guess what a saturated fat is?
and hydrocarbon. And
It's-
alkane.
It has a long alkane chain on there, right? That has a bunch of carbon-carbon single bonds. That has a maximum number of hydrogens around it. An unsaturated fat has at least 1 double bond in there, okay? And then if you read on some of these specialty labels, they have like polyunsaturated fats, right? All these kind of things. And then you have multiple double bonds in there. Good? A couple of points to make. Why did I put the double bond in red there between those 2 carbons?
Draw attention.
I didn't say why I used red. I mean, why did I specifically put it between those 2 carbons? How do I know that it's between here as opposed to in between here or here or here? You guys get the question that I'm asking? Could I put that double bond between any of those 2 carbons as long as I move the hydrogens around?
Yes?
The answer is yes, right? So for instance, if I draw this instead, right? I'll put my double bond here. Is that still a valid structure based off of the formula?
Yes?
Yes. So what would we call it if we have the same formula but a different connectivity? Different
An
set of
isomer?
bonds? It's going to be an isomer, a constitutional isomer, right? So it'd be just like what I asked you guys the question at the end of the last class where I said, hey, draw C5H12. And then I said, draw C5H12 and draw C5H12, right? We're drawing different ways of putting together the same formulas. Good? So we can have the same issue here. In fact, we can draw even more isomers with C5H12, excuse me, C5H10 than we could with C5H12. All right? I'm not going to make you guys do it. But, now, I want you guys to draw me C5H10, but an isomer that doesn't have a double bond in it. How could we do that?
Wait, sorry, can you repeat the question?
I want you guys to draw me C5H10, a valid C5H10 that doesn't have a double bond in it. And if you guys remember, somebody got super excited about this in the last class. Right? Super excited about drawing these. How can we draw C5H10 without any double bonds in it?
This seems like a trap.
No. Everyone always assumes that
Oh,
I'm like
green.
nefarious. You guys always think I'm like out to trick you guys.
Are we wrong?
Yes. Stuff's already tricky by itself. I don't have to add to it.
can I just be like, we can use a shortcut drawing? I'm tired of writing H.
Hmm?
Can I just use the shortcut drawing method, cause I'm tired of writing H?
Sure. I mean, I'm not in charge of your notes.
No, but I'm holding them up for you to see if that's right.
Nothing but the middle. Life is strange, huh?
Okay, apparently I can't draw a pentagram.
All right, you guys got it.
Neither are seeing.
Looks like you guys got the answer. The answer is, right? Carbon, 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 right? Oof, hopefully you guys drew it better than mine, but.
No, I had to draw a devil's pentagram to get the right shape. Pentagrams are very difficult to draw.
It's not a pentagram, it's a pentagon, right? So.
Okay, you, pens, pens.
Right? Question. What type of molecule is this? We only have carbon-carbon single bonds, right?
Now,
So this would be called an alkane, right? But it's in a ring, right? And a ring meaning that the carbons join together, right, to come back and, you know, form a ring. I don't know how else to describe. I think can you guys see that that's a ring, right? I was about to talk myself into a hole there, like, it goes in a circle, like, you know, right? Right? So we would call this a cyclo alkane. So whenever you guys see the prefix cyclo, right, we're just talking about there is some kind of ringed structure in there is what it is, okay? But you'll notice that these cycloalkanes have the same generic formula as alkenes do, the C5H10. That's why what I said is that C5H10, or excuse me, the C5, let me try this coherently. When we have the formula CnH2n, it means we have a deficiency of hydrogens, okay? So a ring also is hydrogen deficient, okay? We do have the maximum hydrogens we can put around there, but because we make a ring, we have to get rid of 2 of those hydrogens is what it is. So be careful, alkenes and cycloalkanes have the same formula there, okay? And so we would consider those isomers, although they're very different, right? One's got double bonds, one's a ring, all these kind of things. Okay? Now don't worry, okay? When I ask you on an exam to draw something for me, I will specify this, right? I'm not gonna sit there and have you guys draw 15 different isomers of C5H10. On an exam, I said, but we're not on an exam, right? We're in class. And I've got to pad this out for another hour, right? So I want you guys to see if you can come up with another ring that has a formula C5H10. Or if you really want to think, there could be at least, let's say, there's at least another three, I hold up 4. I'm good this morning. All right, yeah, geez, I need more coffee. There's at least another 3 rings you could draw with this. Tricky stuff. See what you guys come up with, though. See what other rings you can come up with C5H10.
is there a minimum number of carbons required to form a ring? Like, can you not drop below 5 and still have it be considered a ring for the connections?
Well, rings for us are just carbons that kind of bond back to themselves, right?
Okay.
So the answer is yes to part of the question that you asked there. Now think of your geometry. That's where I would start. Mm-hmm. Be careful, hydrogen's only ever going to have one bond to it. Right? And the way I would approach this is think about different ways that the carbons can come together and then fill in the hydrogens around it. Good. Right? So now you see there's the ring, right? And then you have something coming off of it instead. Can you think of another one? Or no, that's it, right? That's enough thinking, Dr. H, it's already, it's early in the morning.
What carbon does it look like?
Be careful here. Yeah, not with the formula that we have, right? That's okay, we'll learn a shorthand here in a minute. Good. Mm-hmm. Could you think of a different one of this though? You got the right idea, but be careful. You're gonna have the wrong number of hydrogens you got that double bond there. Yeah. No, that's fine. Think of another one of that. You're right, but think of see if you can come up with another structure.
Did you do 4 carbons in the branch?
So no 4 ring?
No, that one's okay.
No,
No.
this one, I mean.
I know, that one's okay. There's nothing wrong with that. I said they're fine with saying, can you see if you can think of another one? That's all.
Oh.
Just you need to, think and come up with something, right? That's all. As you guys figured out, right, we can march our way through our geometric shapes here, right? So we know that if we're limited by C5, we can't make a ring bigger than 5, so we step down, right? From 5 we go down to 4, so we're at a square, right? When you put a carbon coming off of there, if we count up the number of hydrogens, right? We're at C5H10 still, right? That looks good. We can take another step down. We can make a ring, right? You could put one other carbon coming off of here and put another carbon coming off of there. That would be fine. If you guys will pardon me, I'm getting tired of writing a bunch of hydrogen, so I'll just put the green lines there.
That's completely understandable.
Is that still cyclopentane?
No, and that's what I'll get to in just a minute, right?
That would be,
Right? 5 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens on that one, right? Well, we could even go a little bit further into the absurd if we want to think about it. Right? Well, not absurd, just weird looking to me.
would that be 1, 2 cyclopropane? Would that be how
Close. Right?
that's named?
Close. We could stick with the 3-membered ring there, the triangle, and put the 2 carbons off of each other, coming off of one of the carbons, okay? So just as a quick point, I don't want to go too much in depth with this for this class, because it kind of steps a little bit into a broader topic. But let's take a look at this one here for just a second. So there's my 3-membered ring, right? Well, maybe. Okay? And you guys saw that I put the 2 other carbons coming off of the top and the carbon to the right there. You guys with me? So we have our ring, we put it coming off the top and to the right. What if instead I just went crazy, right? And I put the carbons coming off the top and to the left? Is this a different structure?
No.
And the answer is no, it actually isn't, okay? So what we have to start to think about, or one of the challenges that does come along with organic chemistry, is we have to realize that what we're drawing on paper is mostly a lie, right? Your notes are all wrong. Just tear them up and let's start over.
Tape is a lie.
Right? But we have to remember there's a couple things that go on, right? And one of the things that we will start to talk about is just remember what we're doing is trying to represent a 3-dimensional structure, right? On a flat, plain piece of paper. And so there's a couple of, let's say, assumptions that we have to make when we do that. If you guys remember in the first semester of Gen Chem, one of the things we talked about is the idea of resonance structures. You guys remember that?
Yep.
Right, and resonance structures, the way I like to describe it, is we're taking a snapshot, right, of how a molecule looks at an instant in time, okay? And that's sort of what we're doing here. We're taking a snapshot of how this molecule looks at an instant in time. Think about this. So in your coffee right now, you've got a bunch of water molecules, right? You guys could draw water. You guys could tell me about the hydrogens and the hydrogen bonding and the oxidation states and the enthalpies of formation, and you could calculate how much heat gets transferred,
We know how to
right?
do
You
that.
guys can all do that, right? You're getting recorded, so just look, impress the 10 people who are gonna watch this, right? All of you guys can do that, yes? Oh, yeah, okay, good.
Yes, do I want to do that right now?
Right?
No.
The point being, you guys learned all about these things. But one of the things that we step away from when we get, is we have to think about how the molecule, how that individual water is actually behaving. So remember, right, if I talk to you guys about thermal energy, you would say it's the energy of motion, right? It makes the molecules vibrate and move and rotate and bend and stretch and all these kind of things, right? That's how thermal energy is stored. How do you draw a molecule stretching, bending, rotating, twisting on a piece of paper? You don't, right? But the point being is that these molecules can rotate their bonds. They can flip, they can tumble, they can twist. And it doesn't change what the molecule is. It just changes how the atoms are arranged in space. That's all it does. And so the assumption that we have to make, and the thing we have to remember, is we're trying to represent an inherently three-dimensional world of molecules on a two-dimensional plane of paper, right? But you guys are already familiar with this. Because I could ask you, okay, I want everybody to draw a cube, right? Draw a cube in your notes. What you guys would do, right? Is you guys would make a square in the front, right? A square in the back, right? You guys would connect it together, right? And we all look at that as a cube, right?
Yes.
But it's not. It's just a flat piece of paper that we give perspective to. And that's the point that we're making here, right? We can't draw three-dimensional shapes on a two-dimensional piece of paper. That's the problem, right? So we do have to make some assumptions about the drawings that we put on our paper. And one is that they don't actually represent what's really going on if we had a beaker of these things in front of us on the desk, right? Now you guys know that molecules all have three-dimensional shape, right? How do you guys know that? Well, the easiest thing is to look at yourself. Are you a flat piece of paper?
Yes.
No, you're a three-dimensional shape. How do you get shape? You guys ever thought about that? Like, no, that's a philosophy question. Do I really have shape, right?
Well, see, as organic beings, we have hormones, and those hormones tell our bodies to build in very specific.
That's part of it, right? So whenever somebody asks you, though, do you want to get in shape? You always say, no, I'm already done, right? So you're, thank you. Okay? But we do have to remember that all these molecules have shape. And part of the assumptions, I guess it was the elevator or something, right? And part of the assumption that we make is, well, we have to draw things on a two-dimensional piece of paper, right? But you guys also did learn some tricks like the cube when we draw molecules, right? So question real quick. So if you take a look at every single molecule we've drawn so far, okay, they've been all alive because we haven't been drawing them in the proper shape. Got it?
Yeah.
So let's go back to the simplest of the simplest here. CH4. And what you guys drew on paper, right, was likely something like this, which is a Lewis structure. Right? And there's nothing wrong with drawing a Lewis structure, as long as we understand that we are making some of these assumptions, let's say simplifying matter a bit, to be able to draw something quickly, right? But what are the actual bond angles in CH4?
Tetrahedral.
Well, that's the name of the shape. What are the bond angles actually?
109.
109.
109.5, right? Methane, CH4, is an idealized tetrahedral structure. Okay, and a tetrahedron, right, is a three-dimensional shape. Okay. So if we want to draw the molecular structure here, we would put the carbon in the middle, right? And we would try to give dimension by drawing the wedge and the dash bonds. Okay? And if you remember, the wedge bonds are the ones that come out of the plane, right? And the dash bonds go into the plane. So a tetrahedron, right, is a four-sided, three-dimensional shape, right? That's where the tetra comes from. So if you connected each of the hydrogens together to make, right, a triangle as a face, you don't have to draw this if you don't want to, right? But if you connected all the hydrogens together, and I certainly don't have the artistic ability to do it well, right? But each of those faces there, right, there'd be four of them, and that's where we get the tetrahedron shape from, right? The tetrahedral geometry. You guys remember those wedge and dash things there?
Yep.
Right? And so every saturated alkane, right, is a tetrahedral carbon. And its ideal bond angles are 109.5, right? So, knowing all that, let's make life annoying.
Yay.
But don't worry, we're getting to somewhere that makes life easier too, okay? So now, after saying understanding and remembering perfectly how to draw tetrahedral geometries, right? Because you guys had the best, well, some of you guys had the best Jim Kim 1 teacher.
Yeah.
Yeah, you were in the other class, right? So I'm joking. I just got to pick on Dr. Tom every once in a while, right? So, wait, you were in the other class too, weren't you? No, were you Jim Kim 1? I forget, were you? Yeah, no, you weren't, right? Sorry. Okay.
You don't remember if you've had to deal with me for one semester or two?
Tell me the last year hasn't blended together for you guys also, right?
It's been a pretty massively crazy year
Yeah.
for me, so no, I remember most of it just because
What
it's been
is
borderline traumatic.
For what? I think I'm missing one though. I think that one now. Is this from throughout the year?
That's from last semester.
Oh, really?
So if I was a jerk and asked you guys to go through and draw the complete three-dimensional structure for C5H12, right, you'd want to go through and represent it completely in three-dimensional shape, right, with these wedge and dashes there, okay? Now we can make life a little bit easier for us by making all the carbons in the same plane, right? But then we'd have to go through and add the wedges and dashes and lines for each of the hydrogens that are in there. But notice how we start to draw this, right? If you take a look at just the carbons here themselves, right? You saw that previously we drew them all in a straight line, right?
Mm-hmm.
But now we start to put a little bit of a bend in there to more accurately represent as best we can what the actual bond angles are, right? You guys with me on this? Now imagine that you're a chemist, and we don't deal too often with things that are C5 only, right? We have these large complex molecules. So imagine instead I asked you guys to draw C20, right? H42 instead. Say, okay, ready, go. And you guys are like, I think I'll pass on that, right? Right? But the point being, it takes a long time to draw these carbons and put the hydrogen in there and do all these kind of things. And so, as a chemist, I'll go ahead and admit that I'm lazy. But just like you never want to tell the complete truth on your resume, right? Don't ever put you're lazy on your resume. That sounds bad. What should you put instead?
I'm an efficient worker.
You're time efficient, right? That's what it says. That's right. That's how you sell yourself, okay? So we're not being lazy and we're not taking shortcuts. We're maximizing time usage by being efficient, right?
Yes.
It's a lot, right? We're being lazy. Right? So here's what we do. If I want to represent C5H12 as a proper molecule, we can do a shortcut. You ready for it?
Yeah.
Here it is. Done.
Woo!
Got it?
Yep.
Can you guys start to see how one can get drawn into the other, or where we get our shortcut method from?
Yep.
Okay. So what do we do? Let's break this down for just a little bit here.
These angles are the same.
Right? So this is our, I think the book calls this like line notation or line stick notation. I forget exact term that they use for it. This is just a shorthand method that we draw organic molecules with. Okay? What do we explicitly show? We explicitly show single bonds between carbons. Those have to be explicitly represented. Okay? We explicitly draw any bonds in between carbons. Got it? So if we had double bonds, we draw that. If we had triple bonds, we draw that, right? We'll talk a little bit about that stuff, okay? What do we leave off, or what do we shorthand? At the beginning and at the end, where lines come together, okay? At the beginning of lines or at the end of lines, where lines come together, that's where our carbons are, okay? So at the, I think what they call it, the vertices or the joints in the bonds, that's where our carbons are. Good. Now, what's the most glaring thing that's missing? Our hydrogens. And here comes back to one of the first facts I said about organic chemistry. Carbon and hydrogens are best friends. Okay? One of the other important things I said is that carbon will always have 4 bonds unless there's something special going on. Got it? Let's think here for just a second. This carbon right here. How many explicit bonds do I see? 1, 2. So how many implicit bonds must there be? If I see 2, there must be another 2 that are understood. And one of the rules that we said is that we have to show bonds between carbons, but we have understood bonds to hydrogens. Got it? So if I see 2 bonds to a carbon, I know I have to have 2 bonds to a hydrogen there also. In fact, I know I can just fill in as many hydrogens as I need to get up to 4. Got it? So, let's do a little bit of practice. So go back to some of the examples that we just did. Okay? With our rings there. See if you guys can turn what you drew into our shorthand method. Okay? Remember, explicitly show the bonds between carbons, and then our hydrogens are understood. Good. Yeah, right. Good. All right. Man, you guys are making this look easy, huh? Imagine if we could just go into organic chemistry right now.
I think I
Right,
can.
just keep the momentum going.
Yeah.
All right. No, I'm gonna forget everything. By the fall.
Well, it's not like it's offered over the summer.
Not here, that's true. Right? That's true. I'm trying. The honest answer to that is we just don't have the student population for it, right? So if you guys want to go recruit a couple thousand over the summer and bring them on in, right? I think another good 4,000 or so, but you know.
Aren't the jobs
I
already
think that's why
crowded
we
enough?
host the focus groups and all that here over the summer.
No.
We just-
Yeah. So look, if each of you guys recruited 1,000 people, it'd be fine, right?
That would be like a
Yes,
whole
put that on
group
that.
here.
In fact, I got some homework for you guys.
Just
Cool.
use your platform, your large social platform.
Yeah. Like, got 8 people watching, okay.
Like 300 people.
And most of those are like bots that just comment on it. It was great.
I don't know, one time there was an ad when I was trying to watch the lecture. And
Was there really?
No, what?
Oh, okay, no. Like, I was like, I turned that off, like, you know, although,
Put 'em on there. Oh my God.
Can you guys follow this here, right? There's our 3 carbons that are in our triangle, right? And then we have carbon coming off the end and carbon coming off the end. Good. Right. Right? Triangle with the 2 carbons coming off of it. Over here we've got a nice square with 1 carbon coming off of it. You guys starting to get the hang of it?
Yeah.
Right? Now, I'll go ahead and predict the future. Okay? I think the P in PhD stands for profit. Okay? That's, I think, not like PROFIT, like the biblical profit, right? Certainly not the monetary profit. So I'm going to predict what's going to happen. You guys are really going to like to use a shortcut. I know that. In fact, we have to. Right? We just don't have time to work it through everything. But remember, every time you take a shortcut, okay, the job that you guys have to do is remember that there are hydrogens there. Okay? It's very easy to forget those hydrogens. And then when we go through and learn our reactions and all these other things, you guys end up adding too many bonds or having too little and all these kind of problems that come with it. Okay? So don't forget, right? Don't develop these bad habits of forgetting that there are hydrogens there. Okay? Cool.
Andy's got a question.
What's up?
I have a question.
I thought I heard you say Dr. Hillersheim.
No, I said profit Hillshine.
Oh.
Remember, if I'm wrong, it's your job to stone me. I go, oh crap, alright. Ugh, it's tough being a teacher, alright.
There should, Abe really needs to have a thing, like one of those dunk tanks for a professor at one of the festivals. Am I wrong here? Like,
Yes.
I know, I don't think you make the cut, but I'm pretty sure there are some professors that like people would love to see on a dunk tank.
Oh, I'm sure I'd be on that list.
I doubt it.
So see if you guys can turn my structure back into how many carbons and hydrogens there are, right? So let's just go in the opposite direction. So take the shortcut method back into your, let's say your Lewis structure, right? Where you explicitly show all the hydrogens.
That's something alright.
See? The profit was proven correct.
Yeah.
You both forgot the hydrogens. You're missing your H16. 1, 2,
Oh.
1, 2.
Oh, because it's a
4, 5,
frickin'
6, 7,
brain,
8,
dang
9,
it.
yeah.
What's the matter, Joe? What do you have on the 2, 4.
Yeah,
Okay, you're on the right track. That's fine.
I don't know about Joe, but I don't see
Andy, out of curiosity, are you having a seizure?
3.
What's that be on there?
Oh, there he is.
I have an epiphany.
Cool. Looks like you guys are on the right track. Takes a little bit of practice, right? So we'll identify where all the carbons are.
I think that right.
We're at the beginning and at the end of lines, and where two lines come together, right? That's where carbons exist. So let's try and draw that out, right? Carbon, 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 carbon with a double bond to another carbon, right? So remember, we show every bond between carbons and carbons. So if we have a double bond, we have a triple bond, that's explicitly shown in our shortcut, right? And then we do some counting. We see two bonds, so we have to add two hydrogens there. Three bonds
No.
here, so one hydrogen, one hydrogen, one hydrogen.
Hey Doc, I'm gonna make like some atrocious guesses as to the name of this.
Yeah, I don't know. It's okay. Hang on to that.
Cyclo
Yeah.
1, 3, 2.
Blast off. No, this is a tough one to name. We don't have to worry about that stuff.
But I want to know the name for my flashlight.
I'll show you how to get that. Right?
Okay.
Yeah. Good? So take a little bit of time practicing going in between the shorthand and the full Lewis structures, okay? And then, if you really want to get, crazy, right? You could go through and try and draw this as the three-dimensional structures, right? You're like, don't pass.
I do have other things calling upon my
That's
time.
good. Okay, cool. So that's where we'll end it for today. I think that's a good place to stop. Next time we'll just wrap up on one last topic or so, and then I think we'll call it in terms of the new knowledge, right? Because we just have, Wednesday of next week, right? What it is? Alrighty. So don't forget the quiz, right? If you guys haven't already tackled that.
Yeah, I
Who's talking about at 8 in the morning?